Hi, welcome to Chapter 8 and 9, Bonding Continued, where we're actually going to start Chapter 9 today. This is going to be our overview part 4. We're going to talk about molecular shapes and the Vesper model today. So molecular shapes. What different shapes can molecules take? Why do they take these shapes? Why are these shapes important? So these are the main 3 questions we're going to answer in this presentation today. So let's talk a little bit about molecular shapes. We've been doing Lewis structures, and they are very helpful, but they are only 2-dimensional. So a Lewis structure really doesn't show you anything about the shape of your molecule. Okay? But we can use Lewis structures to determine the shape. So we have to draw our Lewis structure, and then from there we can figure out what the shape of our molecule is. Here are some very common shapes. So here is a linear, bent, trigonal planar, trigonal pyramidal, and T-shape. So what determines the shape of a molecule? Really, when it comes down to it, it's all about the electrons. Okay? The electrons that are lone pair electrons and bonding electrons. Electrons repel each other, and they want to be as far apart from each other as possible. And in doing that, they develop the shape of the molecule. Because these electrons here want to be as far apart from these electrons that are in the bond here. So they push away from each other, developing the shape of the molecule. If you want to get really specific, though, the bond angles and the bond lengths determine the shape and size of the molecule. But what determines those bond angles and bond lengths? The repulsions of your electrons. And that's where Vesper model comes in. Valence, shell, electron, pair, repulsions. Because they are repelling each other, they dictate the shape of your molecule. The shape of your molecule plays an important part in how reactive it is. By looking at how many bonding and non-bonding electron pairs you have, you can easily predict the shape of the molecule and how it will react. So the first step in determining the shape, you have to draw your Lewis structure. Then you have to count your electron domains. What is an electron domain? An electron domain is anything that is sitting on your atom, your element. It could be a lone pair, that counts as one domain, a single bond, that counts as one domain, a double bond, that's one domain, and a triple bond, that's one domain. So looking at this example here, element A has a lone pair, so that's one domain. It has a single bond, 2 domains, 3 domains, 4 domains. A has 4 domains. The double bond does not count as 2 domains, it's 1. So it's really just anything coming off the atom. So there are 4 domains coming off atom A. In order to help you visualize how these electrons are repelling each other and then determining the shape, a balloon analogy really comes in handy. So if you blow up 2 balloons that are the same size and you tie them together and then you let go of them, they will form a linear shape. And think about these balloons as the orbitals the electrons are in. If you tied 3 balloons together that are all the same size, they will form this shape because these 2 balloons can't get closer to each other, either or these. They are as far apart or as close to each other as they possibly can. And this shape here is called trigonal planar. If you tie 4 balloons together, you'll get your tetrahedral shape. So once we have our domains, we could figure out what the shapes are. Okay, so if you look at this table here are our domains that we counted. So you have to look at the number of the, well, actually here it is. Here's the number of the domains. So we counted 4 on our example up above. If you remember, it was A. So it had 4 domains. So 4 domains. So the electron domain geometry is called tetrahedral. And think about it. If you tie 4 balloons together, that's 4 domains, that will form a tetrahedral. shape. This here is your electron domain geometry. It might not necessarily be the geometry of your molecule, because say in this case we have a lone pair, so the shape that you actually see will not be tetrahedral. So we're going to get into that in a minute. So how do we get our geometries? We start with our compound, we draw our Lewis structure, we count our domains. So in this case, N has 4 domains. Then we look at our domains and we say how many are bonds and how many are lone pairs. So in this case, we have 3 bonds and 1 lone pair. 4 domains, if you go back and look at the table on the previous slide, for 4 domains, the electron pair geometry is tetrahedral. But in this case, one of the domains is a lone pair. So here is your electron pair geometry. Here's your lone pair right here. See it? When you physically look at the molecule, it's like putting your finger over the lone pair. You don't see it. Do you see a lone pair sitting here? No, because it's not bonded to anything. So the actual molecular geometry is what you see. And in this case, it's called Trigonal Pyramidal. Okay, so you draw your best Lewis structure, you determine your electron pair domains, and that gives you your electron domain geometry, not the shape of the actual molecule, because you have to look at the bonded and unbonded. The bonded atoms will determine the molecular geometry. The non-bonding atoms will affect your bond angles, but they won't affect you won't see them in your molecular geometry. So if you have a molecule with 2 domains is always linear. Linear, 1, 2. Okay? And notice here you have 2 domains and there are no lone pairs. So you could have 2 types of linear, this one right here, or if you just have 2 atoms bonded together. That is also linear. Trigonal planar has 3 domains. So anything with 3 domains, the electron domain geometry will be trigonal planar. Okay, so it's in the same plane, 3 things coming off, okay? That's if all, and then if all of the things coming off your structure are bonds, then your molecular geometry is also trigonal planar. But if one of those bonds is actually a lone pair, so you don't see it, you can put your finger over the lone pair, this shape is now called bent. So for 3 domains, there are 2 possible shapes. Trigonal planar, if it's all bonded, or bent if you have 1 lone pair. Next is our tetrahedral, one of our more common ones. This has 4 domains. And there are 3 molecular geometries you could have. Okay, your electron domain geometry, if you have 4 domains, is always tetrahedral. But what you actually see, the molecular geometry, it could be tetrahedral if all of your domains are bonds. If you have 1 lone pair, then it's called trigonal pyramidal. So if I were to draw it, so here's tetrahedral with all bonds. Now I get rid of one of the bonds because it's a lone pair. So there's a lone pair up here, so you don't see it. So this is now called trigonal because there's 3 things coming off, pyramidal because it kind of looks like a pyramid. What if 2 of them are lone pairs? You don't see the lone pairs, so now your shape is bent, and this is actually what water is. Now what happens when we expand beyond the octahedral? So if expand beyond the octet rule, we could have more than 4 domains. Okay. So it results in 2 more possible shapes here. So we have 5 domains, which would give us an electron pair geometry of trigonal bipyramidal, and 6, which would give us octahedral. So let's look at trigonal bipyramidal. Remember, this has 5 domains now. 1, 2, 3, 4, 5 things coming off. Okay, so this is the electron pair geometry that you'll see. There are 2 distinct positions in this geometry. There is the up and down ones, which the axial positions, and then equatorial is kind of within the plane here. If you have lone pairs, they will occupy in this region first, your equatorial position. So again, this is when you have 5 domains, and you're going to have 4 shapes. If all of your domains are bonded, you'll have your trigonal bipyramidal, and that's what this is right here. If you have 1 lone pair, right here, there's your lone pair, you're going to form what's called a seesaw. If you have 2 lone pairs, that's going to give you a T shape, because it looks like a T. If you have 3 lone pairs, that'll give you linear, just the up and down. You got rid of all of the bonds that were on the equatorial plane. The last one we're going to talk about is the octahedral. Remember, this has 6 domains. So if you have 6 domains, it looks like an octahedral coming off. All positions are equal in an octahedral, okay? And there are 3 molecular geometries that you could have. So if it's all bonds, it's called octahedral. If you have 1 lone pair, it's square pyramidal. And if you have 2 lone pairs, it's square planar, because it looks like a square and it's within the plane. What do you do when you don't necessarily have just one center atom? It's a larger molecule. If you noticed, on all the previous ones, we were determining the shape by looking at the center atom. Well, when you have these larger molecules, you have to kind of discuss the shape per atom or element in it. So like take this molecule, for example. You would discuss what is the shape of this carbon right here, and you would say, oh, it has 4 domains. They're all bonds, so that's tetrahedral. Then you would look at this carbon. It has 3 domains. They're all bonds, so that is trigonal planar. Then you would look at this oxygen, and it has 4 domains, so that is tetrahedral for your electron pair geometry. So you look at each individual atom. But if I wanted to know what would happen, so this is all your electron pair geometry, but here I have 2 lone pairs. So you're really not going to see that. So you're going to end up with a bent part. And notice it's bent here. This one looks like tetrahedral, this one looks like trigonal planar, and this is bent. So let's do some practice. So let's write the electron domain geometries and the molecular geometries for each of these compounds. So the first thing we need to do is count our domains. So for this methane here, it has 1, 2, 3, 4 domains. 4 domains, the electron pair geometry is tetrahedral. And since they're all bonds, the molecular shape is tetrahedral. So now let's look at this one. This one has 1, 2, 3, 4 domains. So it's electron. I'm going to just use electron instead of writing electron pair geometry. And that is tetrahedral. And I'm going to put MS for molecular shape. We have a lone pair, which you don't see, so that would make it trigonal pyramidal. Okay, remember we count the domains on the center atom, so carbon has 2 domains. That makes this linear. They're both bonds, so both the electron pair geometry and the molecular shape are linear. Bromine here has 1, 2, 3, 4, 5 domains. So its electron pair geometry is called Trigonal Bipyramidal. One of them is a lone pair, so its molecular shape will not be trigonal bipyramidal. It'll be seesaw. I spelled that wrong, 2 E's. Here we have water, 4 domains. Its electron pair geometry is tetrahedral, but 2 of them are lone pairs, so its molecular shape will be bent. 3 domains. This will be Trigonal Planar. And its molecular shape will also be trigonal planar because it's all bonds. This has 3 domains. They're all bonds, so it's the same thing as this one here. Our last one has 1, 2, 3, 4, 5, 6 domains. So its electron pair geometry is octahedral. But 2 of them are lone pairs. So that gives us square planar as our molecular shape. So we talked about shapes, but what about bond angles, okay? Why do bond angles get smaller in the following molecule? So let's look at this. So here, tetrahedral. Both electron pair and my geometry. Here, my electron pair. So electron and molecular shape, both tetrahedral. This one has 4 domains, so its electron pair geometry, let me just erase that, is tetrahedral. But you have 1 lone pair, so it's the physical shape of the molecule is trigonal pyramidal. And here again, 4 domains, so it's tetrahedral for your electron pair. But 2 of them are lone pairs, so that gives you bent. What do you notice about the bond angles? So here for your, when you have 4 domains and they're all bonds, the bond angle is 109.5. When you have 4 domains but 1 lone pair, what happens to your bond angle? It shrinks a little. When you have 2 lone pairs, what happens to your bond angle? It shrinks even more. And it's really described here. So here you have bonding electrons. Here you have lone pairs. Lone pairs repel more than your bonded ones. So because this is repelling more and this is repelling more, it's pushing these 2 guys together because this is repelling it more, pushing hard on it, pushing the angle here and shrinking it. So when you have 1 lone pair, it pushes more and it shrinks it about 2 degrees. But when you have 2 lone pairs, it shrinks it a little bit more, so it goes down 2.5 degrees. So non-bonding or lone pairs repel more because look at their orbitals are much larger. So the repulsions are greater and they tend to compress the bond angle. Let's look at this case. Here we don't have any lone pairs, but we do have a double bond compared to a single bond. And what do you notice is happening? In this case, if you have a double or a triple bond, they have larger electron domains than just a single bond. So since this domain is larger, it's going to repel more, and it shrinks this bond angle right here. Okay? So double and triple bonds repel more. So they will make this bond angle larger, but this bond angle smaller. So since they are repelling more, they're going to make, I don't know exactly how to say it, this bond gets larger, but this bond angle gets smaller. And that is the end of part 4.